This is the screencast for section 2.4, example 2. We're going to look at the slope of a secant line, which in example 1, you already know that the slope and average rate of change are the same, so we are talking about that same thing. This time the difference is we're putting it into an application. Growing Drosophila in a laboratory. Was that right? Okay. Use the points P, which is 23,150, and Q, which is 45,340, in this figure here to compute the average rate of change and the slope of the secant line PQ. Well, we know that they are the same. Now we just get a unit to label them with at the end. So we'll look at the change in output, which in this case is labeled P, divided by the change in input, which is time, labeled in T. So output is number of flies. So delta P over delta T will be 340 minus 150 over, and then delta T, the change in time, is 45 minus 23. So I get 190 over 22, which is a total of 8.6, and then the label on this unit is flies per day. So although the flies per day are not changing at 8.6 every day, they're changing more sometimes and then less sometimes. If you change by 8.6 flies every day, you will get from point P to point Q. It's an average. Now try problem number 7, accelerating from a standstill. The figure shows the distance time graph for a 1994 Ford Mustang Cobra accelerating from a standstill. I happen to be a Camaro girl, but whatever. Estimate the slopes of the secants PQ1, PQ2, PQ3, and PQ4, arranging them in order in a table. What is appropriate unit for these slopes? Okay, so I've arranged them for you here. I've also labeled the points so that we're kind of on the same page. Those points are an estimate, so I just guessed at what they would be, my best guess. So I'm going to do the change in distance divided by the change in time for each of these P, Q sub whatever points, and find the average rate of change or slope from P to each of those Q points. So I get 43, 45, 46, and 50 meters per second respectively, which makes sense because the slope from P here to Q1 is going to be the shallowest slope. There's the widest stretch of X per change in Y, and that is the shallowest slope. The steepest slope is going to be P to Q4. That is the most vertical part of this curve so far. And that is the steepest slope. Now, not by much. I mean, the difference is only 43 average meters per second to 50 meters per second. So it's not too much steeper, but it is still steep. Estimate the speed at point P. Okay, so if we're going to estimate the speed at point P, if you can look at the change in, or the average rate of change from each of these points getting closer and closer and closer to P, let's see, 43 meters per second, 45 meters per second, 46 meters per second, 50 meters per second. I would say the best estimate would be 50 meters per second. And really, because that was the average rate of change between P and Q4, it would be a little over 50 meters per second. That's my best estimate for the instantaneous speed at point P.